In the next subsection, I want to discuss some lower bounds. These will be mathematically proven impossibility results, showing what is not at all possible with codes. It's not always possible to reach these guarantees. Sometimes these bounds are weak, so they tell you it's not possible with 0 bits, and you say, thanks, I was kind of expecting that. But you're also convinced that 1 bit is not enough, say. What is happening? That's not the window I wanted. Other than that, okay. Back to lower bounds. Sometimes these bounds are fairly weak, but they're at least provably correct. And often this is the best we can get. They're sometimes only go so far and leave a lot in the unknown. Now I made that sound that like the lower bounds are not really useful. That is in the opposite. That's not true. The lower bounds are very useful in giving us thought or building a firm ground on where to look. It's just in this context usually challenging to get matching upper and lower bounds. But without further ado, let's look at this. Before we can talk about lower bounds, we always need a model for what is possible. We need a lower bound is a statement about all algorithms. All algorithms need at least such and such, so and so many bits to correct errors. So that's a statement about all algorithms, about all codes in this case. So we need to say what is a code. You've seen this for sorting. You've seen this previously when we discussed lower bounds. So here the model is the following. We have a stream of bits. So the star means it could be any length. It's a string of unknown length. And we communicate across a channel. This is like what I sketched in the last subsection when I asked the Slido question. So any individual bit might flip from 0 to 1 or 1 to 0, and no other errors occur. In particular, you could imagine other situations, but our assumption here is just that the channel is so that this is not possible. For example, the channel is strictly timed, and you take a signal out of the channel in every time slot and average it or integrate it. So that's triple E questions that I don't want to get into. You convert what you read from the channel in that time slot to a bit, either 0 or 1, and that's all that is. So you never get out of sync time-wise. But bits can get flipped. Instead of the original string, we send an encoded bit stream. And so the sender realizes the encoding from the source to the coded text. That's the same terminology as in the compression chapter. And the receiver does the inverse and hopefully gets the same source message back. Okay, and then the question is what errors can be detected or corrected or corrected. That's the abstract model. It turns out this is too general for lower bounds that I know of. We'll have to restrict things a little bit further. And what we do is we focus on block codes. The difference here is here we had an arbitrary length input stream. What we do now instead is we assume a single message of a fixed length. So we encode k bits at a time. Of course, you can take the stream and break it up into blocks of length k and transmit that individually. That's what applications do. For the theoretical model, we start with a message of k bits. That's the message length. And we encode each message separately with a code word. And that one has n bits. And of course, we know we have to add some bits of redundancy. The block length is bigger than the message length. Okay, so we restrict our attention to one block at a time. That makes it a little more convenient to work with. Now, any number between 0 and n bits might get flipped in the channel, and we have to think about what we can do. If up to everything can be flipped, there's no way we can detect this. So we will only be able to detect a certain number of bit flips, or correct a certain number of bit flips. And how do we detect that something went wrong? How do we detect errors? We can usually find that what we receive is not a valid code word. It's not C of M for some actual message. And if we find that, we know something has happened. And error correction goes a little further. Can we somehow go from what we receive to a closest valid code word? And how many bits can I recover from this if they were flipped? That's the setup, that's the model. Let me switch to the Q&A. So if you have questions about this, pop them in the Q&A. But so far, so good. We start with messages of k bits. We encode them with n bits, a bit more than k. What can we do with it? It turns out a key number for a code is the so-called code distance. And to define that, we need a little bit of terminology. First of all, a block code is just a mapping that takes any message and transforms it into some code word. And it has to be injective. If I give it two different messages, it better produce two different code words. Otherwise, there's no way I can decode that correctly, right? So injective just means it produces different codes for different messages. Then we define this curly C as the set of all code words in that code. So that's, well, this notation, I don't know if this is something you've seen in math. That's just lifting, that's the range of a function. So it's all blocks in 0, 1 to the n, for which there exists a message in 0, 1 to the k. So that's supposed to be curly. So that this block is what comes out of the message if you apply the code. That is what this notation means. A function applied to a set is the set of all values you can get if you insert the elements from the inner set into the function. This is a subset of all the n-bit bit strings by definition. Just because of the injective property, the size of this is always 2 to the k. So we have 2 to the k valid code words, but in a bigger universe of 2 to the n-bit strings. And then we can say that decoding can always just mean finding the closest valid code word. So I'm starting with an arbitrary 2n bit string, and I try to find what's the fewest number of bits that I have to flip, so that I end up with a valid code word, one in this set curly C. Okay, so graphically you can think about this as follows: if there's a code word C here, then there might be other n-bit bit strings. So X is just some n-bit bit string, but it's not in curly C. Then you want to find a way to map that to a valid C. So this one here is a valid one. C is in the code words. And you want to find a way to map that to this, to the closest valid thing. So if the other ones are further away, if the next C is here, you find that the distance here is bigger, so you want to map it to this one. Okay, that's what's meant with decoding, is finding the closest valid code word. And then we can define the distance of the code as follows. This little d is the smallest Hamming distance of any two code words for this code. So formally, you can write this as the minimum for any x and y in the set of code words, and then take their Hamming distance. Remember, Hamming distance is just counting how many bits differ. Very simple thing. Okay? That's a simple definition, but it has very nice consequences for codes. Namely, if a code has distance d, it can detect all errors with up to d-1 bit flips. Let's try that picture again. So we have a code C. Nope, it's not right. We have a code C here. And now the distance is d, so that means within distance d, there is no other code word. So there cannot be any other C. Then the closest can be at distance d. But if I go only to d-1, there's no other code word in here. So whenever I have a valid code word and flip up to d-1 bits, I end up somewhere in this circle. And so I know something has gone wrong because this is not a valid code word. So I detect that something went wrong. That's that part. Now, how about correcting the error? If I take the same example, here's my C. If I were to draw a circle with d-1 around this, there would be a big overlap between those circles. And for correction, we have to map to the closest code word. Now, if I have something in here, it's not clear whether I should map it to this one or to this one, and I might make the wrong decision. But if I take a smaller radius, just d-1/2, then let's call this t. So I can make a radius of a ball of size t. Then I'm guaranteed that these don't overlap. So the green circles don't overlap. And any of these points inside the green circle can uniquely be mapped to its code in the center. Whereas this blue point here, it's too far away from any valid code word to be sure which one it was before all those bits got twisted. Okay? I hope that picture makes it intuitive why this is the case. It's essentially drawing circles around code words in the space of Hamming distance. But it behaves, for all intents and purposes, it behaves the same as if this was Euclidean distance, where a circle is a normal geometric circle. Now we can use these observations to prove lower bounds on the block length. So we can fix a certain message length k and show what is the smallest n, the smallest block length that can achieve a correction of 3 bits. Okay? Because I can use this mapping to translate between how many bits do I want to detect correct, bit flips do I want to detect or correct, into a code distance. For example, if I want to detect a single bit error, I definitely need at least distance 2, right? And if I want to correct 1 bit, so maybe this is something that's worth writing down. For detecting 1 bit error, we need distance 2. And for correcting 1-bit errors. We need distance 3. Because then 3 minus 1/2 is still 1. Rounded down is still 1 at least. Okay, so for proving lower bounds, we still need an additional argument. So we know what distance for codes to look for, but how can we make that into an argument for the size of blocks? I'll show you two such lower bounds, and the first one is called the singleton bound by a person called Singleton. And it's very simple, which is fitting the name. It says 2 to the k has to be smaller than 2 to the n minus d minus 1, where d is the code distance. So that means no matter what you do, you need a block of at least k plus d minus 1. So you have to add at least d minus 1 bits to your code to get a certain error detection. Well, to get, no, this is the distance. You need to add at least d minus 1 bits to your message if you want distance d. Okay, before we discuss the proof, let's apply it to a simple case. Say we have 100 bits, like in our example before. We want distance at least 2 to detect 1-bit errors. So that says n must be at least 101. So we have to add at least 1 bit. That's not saying that it's possible with 1 bit necessarily, but it says it's not possible with not adding anything. Thanks. Not very useful, but it's a valid lower bound. If we make d a little bigger, then it becomes a little more telling. Now, how can we prove this bound? Suppose we write all the 2 to the k code words underneath each other. So this is C. They all differ in at least d positions. So whenever I take 2, I can find d positions where they are different. But of course, these positions can be different between any pair. Now, what I'll do is I'll take away the first d minus 1 positions and just look at the remaining code words. Because I only take d minus 1 away, I still have at least one of the mistake positions, the differences, still in the remaining one. So even if I delete the first d minus 1 bits, the remaining code words are still all distinct. They might only differ in 1 bit, but they're all different. But there are only 2 to the n minus d minus 1 such shorter bit strings just by counting. And that's all the bound says. It says if I want to have distance d initially, then 2 to the k can be at most this, because that's what's left after deleting the first d minus 1 bits. It's a very simple argument and a very simple bound. It's also a fairly weak bound, but it's occasionally useful because it can nicely be rewritten in terms of a bound for n and not just an inequality that we have to check by inserting numbers. The second lower bound is the Hamming bound, and it has a bit more of a more complicated form. So these are binomial coefficients. Read about those on Wikipedia if you've never heard about them. But without discussing the details, the idea is to count how many things we cover with balls of a certain size. So we have 2 to the k code words, and each of these code words is a center of a circle. And I take, again, this d minus 1/2. So I have these non-overlapping circles. Okay. And one more. I wanted to have this in red. Oh, come on. And the circle around it. So this is with length t, as given here. So we know the circles don't overlap, they don't touch. There's no element that they share. So that means if I count how many elements there are in this circle, and that's what's done here, including the red one, and I multiply the size of this ball with the number of balls, I should be able to I get a certain number of bit strings, and that cannot be more than the universe. Otherwise, they would have to overlap. If they don't overlap, they have to all fit into the space of 2 to the n bit strings. I have so many balls. This is the size of each ball, this thing. So that has to be at most 2 to the n. And rearranging for 2 to the k gives you the Hamming bound. So this is again a fairly simple bound, a fairly simple argument to come up with the bound. This requires a bit of counting to count how many green balls there are. You basically count in layers. That's the number of ways you can flip f bits out of n. It's not deep combinatorics, but I don't want to get into the details of this. Okay. And we'll revisit those later. But these are two bounds. This one gives you a nice expression. Your code has to be at least that long. This one only tells you if you insert n, k, and d, and this bound is violated, good luck finding such a code. It doesn't exist. If you insert your n, k, and d and it comes out true, it says this might be possible. It doesn't guarantee that it is. It's only a lower bound.